So let's move on to the presentation tonight. Martin Kwong has been a member of the Fort Wayne Astronomical Society since, I believe, about November. Martin is a graduate of the United States Naval Academy with a BS in oceanography. Navy and oceanography, that seems to go together. So
that's actually why I chose it. Was because I was a Navy.
He has an MBA from the Cornell Johnson Graduate School of Management. Are you still finishing your master's degree at Johns Hopkins, or is that done?
That's halfway done.
Halfway done.
Yep.
Well, still, it's a very prestigious school. The focus of the master's degree is electro-optic space systems. In other words, it's basically weather satellites and space telescopes, right?
Yep.
Basically. He also served 7 years in the Navy as a supply officer for ship and aviation logistics, and is currently at L3 Harris working on the optical payload for the next generation NASA NOAA imaging system and the Japanese Himawari-10 geostationary imager.
With Ben here.
And all of that going on in Fort Wayne. So it's a pleasure to have Martin here tonight to give us some insights into the design challenges of space optics. Now, space optics still sounds kind of wild and esoteric, but it's as familiar with those simple machines called the Hubble Space Telescope and the Webb Telescope. So how much simpler can it get than that? Yep. Martin, thanks for coming tonight.
Thank you.
Tell us all about it.
All right, so I'll get started. Thank you everyone for coming. So this is a passion project of mine that's been going on for a while. I started making this presentation for Science Central, and the kids really liked it. And so I decided, I would like to grow this into something that could be educational for everyone of all ages, right? Because as I was learning this stuff at L3 Harris and through education, I thought to myself, I wish someone would make a format that was just user-friendly, because it's just you're learning it through physics class, you're learning through electro-optical class. It just comes heavy, and you kind of have to find a way to understand it. And so I was like, this would be something. So I've been working on this as I've been doing the class. All right, so some of the topics, right? So I'll give a quick introduction myself, but I want to start off by building everyone's fundamental knowledge of light, right? What light is, then to photon capture. How does the camera work? Why do we need to focus light down? Why is all that important for what we're doing, right? Why are we using space? Why do we care about low Earth orbit, geostationary orbit? In this case, we'll focus on geostationary orbit, but it was a common concept, right? We'll go a little bit about the history of GOES, right? The program that we know today with the Advanced Baseline Imager, but it started in 1975. It's been going on, and there have been marked improvements in the decades since 1975 to modern day. And then, of course, into the future, we're working on now GeoXO. GXI is the imager for GeoXO. That's going to have improvements as well, right? Talk a little bit about the Earth observing fleet. It's a cool little slide. And then we'll go over breaking down the optical elements, which I think is a lot of tie-in for telescopes, because there's optics we'll go over here. There's a relationship to just optics in general. We'll talk about the Advanced Baseline Imager, which is what you will find on the GOES R series, GOES 16 through 19. Some of the risks and challenges, right? And that's important because Ben pointed out to me earlier, quality is a huge challenge and concern with space optics. You're talking about an environment, an orbit where things are going 15,000 plus miles per hour, and then also launch itself can cause the risk of misalignment for optics. It's just a very difficult environment. And then I'll close with some more applications of infrared optics, and we have time maybe to take some questions at the end. But the material I do have to focus on the material while we're talking. So I'll reserve some of the questions for the very end. All right, so a little about me. Project engineer on the GeoXO sensor unit at L3 Harris. I also work as the project engineer on the Himawari-10 as well, specifically for mechanical, sensor unit mechanical. I used to handle the procurement and running the design team for the aft optics as well. So a lot of the things you would think of, the beam splitters, some of the filters and whatnot, but now we're focused on mechanical subsystems. I was introduced earlier, oceanography, graduated in 2014, then served 7 years in the United States Navy, and then got my MBA while I was, when I got out of the Navy. And then Johns Hopkins Space Systems Engineering, how this came about was L3 Harris was willing to sponsor me to get that education. And I just made sure to make it focused on, scientific instruments and electro-optical space systems. A lot of overlap there, but yeah, I already got the introduction, so we'll move into the subject. All right, so what is light, right? I would always open by asking people, the kids, what is light? But I think I'll just kind of go into this about light, right? So I'm going to give you a bad definition, and I'm going to correct this definition. Encyclopedia Britannica, light, electromagnetic radiation that can be detected by the human eye. That's fundamentally wrong, right? Because we know that light occurs over an extremely wide range of wavelengths, stuff from gamma rays, from very short wavelength, billionth of a meter, all the way to radio waves and microwaves, which are over a meter, right? So that's why that's wrong. But it's good. I wanted to do that because a lot of times we take that for granted. We think of light, we think of the light we see, that it's dim here, it's light over there. So okay, we see light, but there is a whole spectrum that we can't see, what we can detect with instruments. And here's just kind of like a you talk at your spectrum, you're going from your high energy and short wavelengths and high frequency all the way to the right-hand side, which is going to be your long wavelengths, low frequencies, and lower energy. And by energy, I mean photon energy, right? We'll get into that in the next slide. So big thing to know is that, most of this is invisible to the unaided eye. We have a very narrow visible spectrum right here between ultraviolet and infrared, which we can see, which makes up those colors of the rainbow, right? So use a prism, but also there's a diffraction grating in here as well. But basically, visible light is actually made up of many bands of light. Right? You shine, whether it's the light from the lights in here or a flashlight, you can actually split it up into its bands through either refraction or through diffraction, right? So there's two different ways. You see, you got a prism here, which is white light comes in and you refract based off what we call index of refraction. So the bands bend. So what happens is that the higher frequency, which is your ultraviolet and higher energy, bend more, and then the lower frequency bends less. And that's why you have your ultraviolet, your violet, and your blues up here, and then your reds down here. And then also with the diffraction grating, right? Diffraction grating, you think of if you have like a sheet which has just many small grooves in it. When you shine a white light on it, it causes a kind of a phase shift in that light. And so what happens is that you have constructive and destructive interference, and we'll go into more of those terms a little later, which then allows you to see those individual light. Now I want to turn over to this this right here, right? So this is a lot more detailed than the spectrum we saw before, and this is on the visible spectrum. And the reason why I added this in here is because it shows some key relationships that we want to keep in mind, right? So on the left-hand side here, we have our violet, which is the highest frequency, 750 terahertz, right? 10 to the 12. And then you have your wavelength, 400 nanometers, 400 billionth of a nanometer. So 400 nanometers, a billionth of a meter. Sorry about that, getting confused. Your photon energy, which is 3.1 electron volts. Interesting thing I want to point out is that we measure photons in this case in terms of electrons, right? That's something to just keep in mind, and we'll go into why a little later. And on the other side, the relationship, lower frequency, 380 terahertz, the longer wavelength, 780, and the lower photon energy. And this is the energy for a single photon, a single unit or particle of light. So a couple things like that we pointed out. And also a laser, if you shine a laser in a prism or a diffraction grating, it's whatever the color of the laser is, that's the color you're going to see, right? That's because it's not white light, it is a coherent mostly single wavelength source of light. All right, so continued, what is light? Light is a wave. Now, I know some people before getting into physics will say, I know, Ben, you're going to do that, but let's start off defining it as a wave first, right? So key experiment back turn this over 100 years ago, Young's double slit experiment. So what did this experiment show? This experiment, very simple to set up. You shine a source of light through two slits, and what happens is that when the light comes out, you have a series of fringes or interference pattern that shows up on the backing surface or the wall, which then led scientists to believe that, okay, so once you split that single light source into two light sources, it's basically one wave turns into two waves, and then they interfere with each other, and then they cause a fringe pattern on the wall. And if you think about it this way, think about I dropped two rocks in a pond, a left rock right here and a right rock right here. If you think of the ripples that come out, right, and if they before they hit the wall, like the wall behind the in front of you, they would have this interference pattern because there are areas of constructive and destructive interference. Waves constructively and destructively interfere. Some areas become more intense and some areas become less intense, and that is what leads to this fringe pattern. So think of light like a wave. Then you take a single source of light, break it into two waves, and then you have this propagation of waves, which then causes interference pattern, right? So that's the first thing, right? So we're building light as a wave first. And here's some examples, actually. So this one is one I did at home. But as you see, if you take a strand of hair and you split a green laser beam, you actually have this interference pattern. So what is this leading you to believe? That, there's these waves that are just interfering with each other. And here's an actual picture of someone who created a situation where you can actually see the interference pattern in the air, right? So there are areas, you see the fringes, areas where it's high and low intensity, all right? So defining it as a wave first. So light, okay, so if we get it as a wave, light is a particle, right? Light is made of photons. So here's what happened, right? So people were convinced that light is a wave. Then we said to ourselves, okay, well, all right, it's a wave. Well, then something happened, right? We did we observed light as a particle through what is called the photoelectric effect. And this is basically photons hit usually a metallic surface, knock off electrons, and the wavelength and energy of the photons will actually determine the electrons that are being knocked off of the particular metallic surface in question, right? So like, okay, this is interesting phenomenon. Here you have an example. Photon comes in, knocks off some electrons in a like say metal plate, and you have those electrons exiting. And we know this happened because what we would do, we find out that once you shine a light source on this plate right here, as long as there's intense enough frequency, right, a high enough frequency and enough energy, you knock off electrons and they cause an electrical current. And that electrical current can be measured. And then that's where we started saying, okay, this is the photoelectric effect, right? When we talked earlier about, measuring photons in terms of electrons. So this is an example of being able to tell a photon's inherent ability to knock off an electron, or, be able to model that, right? All right, so now we're getting kind of the little more esoteric parts of light as a wave and as a particle, right? So the duality of light. Light is wave-like and particle-like at the same time, right? So I'll get more into the actual fundamental level of this, right? So light behaves like a wave and as a particle, and works in a probabilistic nature. If you don't measure light, right? If you don't measure, you'll have a wave interference pattern. If you do, you actually see light work more as a particle, right? And this has some implications for the nature of reality. So I have a couple shots in here. I'll try to explain as best I can. All right. So imagine a photon gun, a gun that can shoot photons, or the particle of light, a fundamental particle, one at a time, right? So on the left-hand example, we have a double slit here, to left and right. So photons can go left or right in here, right? If we do not measure or we do not try to observe which way the photon goes, what happens is that, oh, if you shoot this 1,000, 1,000,000 times, it will create the wave interference pattern. And so individually, the photons are forming, over time, are forming this wave interference pattern. It leads some, and Ben can correct me, to believe that the photons can interfere with themselves. Like they exist in a state of probabilistic nature. However, if you add a which way detector, which is just something that says, did the photon go left or go right? And you do the same experiment, what happens? It creates left and right patterns. So it means that basically some photons went left, some photons went right, and they act like a particle, as in, no, you no longer have this wave interference pattern. It's no longer a state of probability. You have collapsed the probability to either left or right, right? But, and so here's a kind of a larger example. I like mine screenshots better because this shows what's happening actually at the particle level. This kind of leads some to believe that the photons, oh yeah, they must be like just interacting with other photons and whatnot. No, at the fundamental level, the photons can do this, can exist in probabilities just by themselves, sending if you don't observe it. All right, so quickly, quantum mechanics. Well, the particle duality, the wave particle duality of light is what you get with quantum mechanics. A lot of interpretations, but the big thing is the Copenhagen interpretation. Everything exists in a probability until it is measured or observed, right? Getting the semantics of the conversation, and then it collapses, right? And then the many worlds, which is another interpretation that says that you don't have a collapse. You just have infinite universes, right? You just have multiple worlds, and because, and I know that's kind of like conceited, saying that kind of conceited way, but like it's a saying is that either you believe in the collapse or you don't. And if you don't believe in a collapse, so that means that just there's branches of probabilities that just go on, and the one we're living in right now is the one that we went down, right? So that gets into kind of the reason why I brought all this up is because it just adds to the complexity of what we're doing with space optics and optics in general. These are all things that we do need to account for. We account for it in ray tracing. We account for it in stray light. There's always a probability. There's always, maybe sometimes you run a Monte Carlo, which is a probability analysis of where the photon can be. Right? So this is why. So here's a kind of example of something I did myself, actually, a double slit experiment, right? So as you can see here, you have your left and right, your double slit, and a light source, which is a 5 milliwatt laser. And then if I don't do anything to collapse the wave function, you have fringes, right? So that means this is the interference pattern on here. And then here, if I add polarized vertically, so horizontally polarized and vertically polarized, which basically means these strips will only allow light to go in either the horizontal or vertical plane. That means I'm forcing a state of the photon. Then you have somewhat of a collapse into either left or right. So the fringe pattern goes away. Now, this is not nearly as fundamental as what scientists are able to do with single photons, but it just shows that there is you can cause a wave function collapse. And so the better the experiment you have, the more of that you can show. And there's something about a quantum eraser. I'm glad y'all look that up. It's a cool little experiment. All right, so now we know how the nature of light, right? So what can we do with light? The basic thing we can do with light is photon capture, which is using that photoelectric effect. So photons to electrons to signal to data. That's the way we're going to go with this. So the first thing is your camera. Everyone has this in their phone. This is how your phone camera works. So on your left-hand side here, you have this thing called a Bayer filter, and this restricts photons that come in to either red, green, or blue. And so you usually have 1 pixel for red, green, or blue. And then, as you can see here, so you have this fruit that sends the light, comes in from off this image of this fruit through your lens. It's focused to this Bayer filter, which then filters down to red, green, or blue. Usually 1 pixel for each color. And then you have a series of analog to digital converters that essentially what they do is they take that you take those photons which hit the sensor, which then knock off those electrons. Those electrons create an electrical signal. That electrical signal can then be converted to a digital signal, 1 or 0, and it can be stored as data on your phone. And every time you snap a picture, that happens like that every time, right? So that's the basics of how your phone camera, but also imaging works, right? Is that you're going from photons to electrons to data. And why is all this important, right? So it falls under this form of engineering called optical engineering or optical physics, and you see it everywhere. TV remotes, high-speed fiber optic cables, and also Earth observing satellites. And then a little thing about it, right? So everything around us, right, gives off thermal energy in the form of, we see it as, we feel it as infrared energy, but we can make detectors that can pick this stuff up and image it, right, under certain conditions. Vapor, clouds, wildfires, hurricanes give off light in the form of infrared energy. And here's an example of a map, of a thermal map or image that we can pull off of the geostationary satellites, right? This is from NOAA. As you can see, the color coding corresponds with the intensity of the infrared energy. So why space? It's real simple, right? So space, the further away you are from something, so this piece of paper right here, if I'm right up on it, right, then my vision is restricted to this. If I pull it away from me, now all of a sudden I see much more. If I am in geostationary orbit, which is 22,236 miles away from Earth's equator, I have a couple key advantages. One, I see all of Earth. Earth is its field of view in my image is 20 degrees, right? It's 20 degrees field of view. So that means I can see the whole thing. Also, I am stationary relative to Earth because the period of orbit around Earth is the actual day, like 24 hours of Earth. So I stay relatively the same spot. Couple key things, right, with that. So I see all of Earth. I stay in relatively the same spot, so I can track a hurricane from birth to death. Also, I have a constant downlink and uplink to the ground station. I can send high resolution data, high imagery data all the way, like, constantly downlink. So gives me ability to, basically create something that can send some extremely high resolution images in multiple wavelengths to the ground station constantly, right? So we have constant comms, with these satellites because of the place they stay, which is stationary relative to Earth. And that's a current generation you see GOES 16 all the way through GOES 18, different regions, right? And all right, so brief kind of history of GOES. So 1975, kind of is the start of the program. I added this little thing right here 50 years ago, GOES 1975 to 2025. So GOES 1 represents the start of this. And couple key instruments on GOES 1, a visible infrared spin scan radiometer. So day-night imaging of clouds and sea surface temperatures, cloud height estimation, and wind field derivation. And then also you had a space environment monitor, so for picking up trace photons, electrons, and X-rays. Very simple, but it allowed us first to actually be able to see what's going on in space from geostationary orbit. And then we go into the 4 to 7, GOES 4 to 7. What this allowed us to do was it gave us the ability to vertically profile the atmosphere, which means be able to see, a column of air, right? Be able to make it like a cake, a column of air, make it a cake, and see what's going on. And that allows you to basically have more accurate oceanographic models of what's going on with the climate and also with the weather. And then we get into the GOES 8 through 12. 3-axis spin stabilization. This is important, right? Because this allows you, finally, if you can stabilize in your X, Y, and Z axes of your satellite, because the thing about this is before that, everything was just, not spin stabilized. This is stabilized. That means now all of a sudden I can keep the attitude of my satellite constant. So my position is constant and my attitude is constant. Now I can point accurately at the Earth and say, I want to see what's going on, there, right? That part of Earth or this part of Earth that, in my field of view. Very important, because what happens is now we can have imaging and sounding 100% of the time, which because we can determine the attitude of the satellite. And then the GOES 13 through 15, we improve on that. We have simultaneous independent imaging and sounding. The reason why this is allowed happens is because our attitude determination control, our ability to know where our satellite is orientation wise relative to Earth and the sun and everything else is much more accurate. And all these advancements then lead to GOES-R, which has all of those advancements, but now it has the advanced baseline imager, which is the gold standard of Earth imaging. And we'll get more into detail of that, but that's kind of the quick history at a glance of GOES. So Earth observing fleet. So I just want you to notice, right? You have your GOES 18, right, all the way through the GOES East here, and these are all the where they are relative to Earth. The red orbits you see here are called polar orbits. They go North Pole, South Pole, and we also have the Joint Polar Satellite System. We call it CRIS, cross-track. It has the cross-track infrared sounder. And basically what this is think of someone's referred to me as like taking, infrared channels and making them like hyperspectral, which means you have taken, if you have like say mid-wave infrared, turn that into 2,000 channels, right? What it allows you to do is now you can like really just get in the details of the column of air, right? From the and see what's happening at every level. So the difference GOES is all about seeing a lot, and then Joint Polar Satellite System, CRIS, is all about being, in this much closer orbit and basically allowing the Earth to rotate underneath you, and then you just get this like very high definition, very just segmented tracks of the atmosphere. So go through a couple, of the some of the elements that make up the optics. So telescope, right? Telescope focuses light to a point. Everyone's familiar with that. We got the Cassegrain, you have mirror anastigmatic types, right? But telescope, focus to a focal point. A mirror reflects light based on incident angle. A beam splitter splits light into separate beams. And I'm going through these quickly because I actually have some real examples we can look at. And absorption filters only allow specific wavelengths of light to pass through. They block out other wavelengths. Right, so you see here, this one only allows 520 nanometers, which is the green light. So this is something I did in my own house. So I have a telescope. I have a light source right here. I have a telescope that focuses light down to a point. So it leaves here and it's focusing down. It enters a beam splitter. The beam splitter splits the light into multiple paths. Now I have separation, right? So I have optical filters. These optical filters only allow light in through these respective wavelengths. So this one is 570 to 780. This one's 400 nanometers to 600 nanometers. You see the actual color of the light. The color of the light is the center wavelength. That is the center light. And then you have these filters here, which then filter it down even more. So this one filters down to 400 to 500. So we take this and make it much more narrower, and now it's violet. And then with this one, this filters down to 660 to 780. So in the very much red, and now you have red. I want everyone to notice something is that it's not perfect. You have this stray light here, right? So this is the challenge, so what we want to do is we want to prevent that from happening. Here you have, just reverse order. You have the narrower, like the narrow filters, and then the long filters here. So 400 to 500, and then 400 to this would be 400 to 600. So only 400 to 500 goes through, right? This just shows that reverse order still works, but you can't mismatch it. So if I mismatch my long pass filters, you're not going to have any transmittance. So this is mismatch. 570, 780 go transmittance, 400 to 500. There's a gap, right? 500 between 500 to 570, no transmittance, except for, of course, a stray light. And the opposite's here true as well, right? And this is just basically shows too, if you mix up the you mix up the orders, you can block light, right? 400 to 500, and then this is 570 to 780. There's a mismatch, so no transmittance. So we got through the basic elements of that, right? That leads us into advanced baseline imager. It's good to have that foundation first. All right, so we have a GOES satellite. We have all these instruments on it. Right here is the advanced baseline imager. This is what this superstructure of it looks like. You can't really see it, but there is an optical port sun shield up here, which light comes in, and it is goes to your optical elements and gets to your filters. Basically, so we're working in the visible, near infrared, mid-wave infrared, and long-wave infrared from 400 nanometers all the way, or 470 nanometers, all the way to 14 microns, or 14,000 nanometers, right? So from visible light all the way to just almost basically pure thermal energy. So here's how this works. Let's say, so we have scan mirrors, north, south, and east, west. Light comes in. Scan mirrors allow us to scan the Earth. The reason why, though we can see all of the Earth, we want to maintain, half to 1,000 meters of resolution. So in order to do that, we're going to have a very narrow field of view, Like, then what's our field of view for roughly, like kind of for like our telescope, like a 4-mirror astigmatic or something. Okay, but let's go with that. So half a degree, right? But we said that from geostationary orbit, the Earth is 20.21 degrees. So we got to scan that half a degree over all of that, right? So the scan mirrors allow us to do that. And then the light from the scan mirror, north, south, east, west, is fed through this 4-mirror anastigmatic telescope, which is basically 4 mirrors that give you ability to have a little wider field of view and actually correct errors or chromatic aberrations, as they call it, like between the mirrors, right? And then that is then sent through a beam splitter, which creates 2 tracks. You have an infrared track and a visible track. Infrared light goes this way, and then visible light goes this way. So we're separating infrared from visible light, right? You have these windows and cold stops which exist to prevent stray light. But the big thing is what's happening here. So your infrared tracks are further separated into mid-wave infrared, 3.9 microns to 8.5 microns, from long-wave infrared, 9.61 microns to 13.3 microns. So what's happening is they're split here, and then in these are called focal plane arrays. These have narrow strips filters, which then cause these individual actual tracks of from 9.61 to 13.3 and 3.9 to 8.5. And then that is when you hit your detectors, and then you have that photoelectric effect. So you can imagine what's happening is that you're creating this cake image from 0.47 microns all the way to 13.3 microns, and just layers of imaging data from visible all the way to long wave infrared light. And that is how this kind of looks this is what the scan is doing, but that's how you get this right here. So this is like a multi-layer image right here. All right, so we want to talk about some of the risks, right? So I know it's very text heavy, so I'll just try to get to the main points. Risks and challenges: stray light, unwanted light. You saw that even from my demonstration, we have unwanted light, just it's inherent. So things you have to look at, to avoid that, because it can give you bad data. Baffles and apertures, the cold stops, blackening some of the material, right? Making an optical design that prevents some of that, right? Maybe like advantages of using the 4-mirror anastigmatic, which is a more complicated system than a Cassegrain. Doing a stray light analysis, to see, okay, well, where do we see the highest risk? That's all important, right? Launch-induced risks and challenges, vibration and shock, right? You could talk about, G's, like super high G's, anywhere from, more than 3 G's at, if like up 3 G's or more. Now all of a sudden you're talking about optical misalignment in your elements, and you have thermal environment changes from, sea level all the way to the coldest space. Now all of a sudden you risk outgassing, which basically means the material itself wants to let out gas as the temperature changes. And so that outgassing, you have to pre-plan before to like make sure none of that actually causes contamination of your optics. And then, redundancies, you have to, mitigation revolves redundancy, robust design. So redundancy means multiple different systems in order to work if case one falls, and quality control. You talk about the environment, right? So one thing that you have to do with infrared optics is you have to supercool them. You have to cool them down to 77 degrees Kelvin, which is liquid nitrogen temperature, in order for them to work, right? So we take that for granted. Our phones capture visible light. We don't we don't worry about that. But long wave and mid wave infrared, you have to cool it down. So now all of a sudden, that's another risk. How do you maintain cryogenic conditions, right? Maintain them for your optics, for your long wave infrared detectors and optics, right? So shielding, radiation shielding, thermal insulation, active thermal control, cryo coolers, right? Like these are all things that present huge challenges all the time, right? So I'd like to end with talking about some of the more esoteric, exotic applications of infrared, right? So James Webb, deep space exploration, looking at the infrared light. And advantages are, if you can see into the infrared, you can see past dust clouds. You can see, photons that have started off at very high energies, and then over time, shifted to redshifted to lower energies. As an example, right? And then from Hubble to James Webb, now all of a sudden with that infrared imagery, you see so much more. And this is not really a color image. They actually color the image in, but it just shows just from infrared, you get so much depth from that. The Nancy Grace Roman telescope, which we've also provided the primary mirror for. Supermassive black hole, collisions, dark energy, dark matter. The best way to think of it is that James Webb is a very narrow focus, very like a zoom lens. And then this is a wide field of view, right? You can basically get a wide swath of the sky and then, see the effects of gravitational lensing, all these things that allow us to understand the universe better, right? So two black holes colliding that's like something that both of these will try to get good information on. And redshift, displacement of spectrum of an astronomical object toward longer wavelength. So there's two things that lead to redshifting. It's like a Doppler shift, right? As something leaves you, if an ambulance leaves you, all of a sudden the pitch, right, becomes longer, right? The longer pitch, and then there's less energy. Same thing happens with light. If it's leaving you, now all of a sudden that those wavelengths are being stretched. The actual fabric of space-time is stretching too. The universe is expanding, and so all of that expanding, right? The universe is that light. If it's traveling long distance, its wavelengths are going to expand as well. So something I could start off as say as an X-ray, over light years, may come to your eyes as infrared, and that's why we need these infrared optics, because they can see basically see things that our eyes can't, even over long distances. And in the future, you got LIGO, LISA, you have laser interferometry, which is seeing how space-time, right, how gravity as waves interferes, and then we can then say, okay, well, if we have lasers, we can use lasers. If they're long lasers, we can determine where gravity is coming from. And and if something like black holes are colliding, they let off gravitational waves. These waves, they're like wavelengths are like maybe a fraction of a fraction of a proton in length. And so you use these long lasers, and now you can see them. These lasers, the LIGO is like 4 kilometers. The lasers are long. In LISA, they're going to be in space. They're going to be like 12 million kilometers, the length of the lasers, right? Some crazy, crazy stuff. We have an engineering development unit. I don't even know how we're doing it, but that's some of the stuff, right? So, yeah, but hey, a lot of material, but I hope everyone got something beneficial out of it. I spent some time on this one. I don't know how much we're doing on time, if we can open to questions or not. Or Joe, is that we got some time for questions?
Sure.
Yep.
Go for it.
Yep.
You're going to comment on the electron volt values, lightweight. How does that fit in?
Yeah, so the electron volt, the way it fits in is we talk about the detectors, right? So every material has something called a working function, and what that is not all light that strikes a detector or material knocks off electrons. It has to be at a a high enough of either intensity or frequency. So even if something like, say, is very intense, like a lot of energy, if it's not the right frequency, high enough energy frequency, it still won't knock off the electrons. The electron volt allows you to determine, you know, based off the electrons, what can you expect when you hit like a substance, like good for detectors, like that photoelectric effect. That's the reason why I brought that up, was to show that relationship that like between photons and electrons, and that sometimes they use electron volts to characterize photons. Yep. Okay. All right.
You want another question, Martin?
Yeah. Oh,
What improvements is the next gen imager? Some primary improvements over the
So improvements. So right off the top of my head, we have more channels. We have more than 16 channels. We're basically able to really stretch out the design of the focal plane arrays to like have be able to take. Essentially, we're maxing out our design. We had some play in the design. Now we're maxing out the channels, and now we can just get more data. So you're able to see more of the detail, right, of what's happening between the spectral range from visible to long wave infrared. So that's one.
Better spatial resolution.
Spatial resolution. Thank you, Ben.
Speed.
Is the footprint the same for the payload?
Yeah, we're using a similar footprint. Yeah, with the focal plane arrays, we're basically just maxing out the design, right? So like after this, we'll have to kind of think about creative ways to get even more out of it. There's one thing I know that we're sending a lot of, this requires a lot of data transmission from space systems engineering. I'm thinking that in the future, we might be looking at maybe free space optical communications, like using lasers to send data, because now you get up to like 10 gigabits per second, as opposed to a couple hundred megabits per second. In geostationary orbit, because we're relatively stationary, it's so much easier. We could just shine a laser, you know, do laser comms to Earth, because we will maintain constant comms. Like there's many different things we can improve on just from the orbit. The orbit gives us a lot of advantages we can take advantage of. All right.
Last question.
The question is, those satellites been, the first one was put in orbit about 50 years ago?
Yes, yep, 1975.
I assume most of the ones are probably non-functional. They've served their limited lifespan, no longer operational.
Mm-hmm.
So what happens to them over time?
So what happens with geostationary orbit, satellites in geostationary orbit, unlike low Earth orbit, where we look to try to use the atmosphere to end-of-life disposal, right? With geostationary orbit, every satellite maintains enough fuel at the very end with thrusters to be able to kick themselves out of their orbit into like either a parking orbit, which ultimately leads to a decommissioning. So we have enough, every satellite, and say like geostationary is too far away to like worry about using the atmosphere of the Earth to like, talking 35,000 kilometers, right? So they kick themselves out of orbit. Yeah, because geostationary orbit is we want to protect that orbit because it's very very advantageous, and it's unlike LEO, it's over the equator. So it's basically this ring around Earth that is 35,000 kilometers away, 35,786 kilometers away from Earth, right? So that's what we do, is it kicks itself out.
I think some of them we sold to other countries too.
But that too, we could do that. Yeah, if they're so good.
I think
But eventually they run out of fuel.
it's used.
Yeah.
It's
Yeah.
Honest L3.
Yep.
Well, no, it's NASA NOAA selling it.
Oh, okay.
Yeah. We've already sold it to the government then.
A lot of money's changing. I've always
Not
been
my area.
fascinated by sprites. Geosystem, can you see them, measure them, the intensity?
I'm not familiar.
Sprites are the electrical discharge from the top of the thunderstorm to
Goes
the
up.
ionosphere.
Okay.
Goes up. Sprites go up, the lightning goes.
There's something with the lightning mapper, or
Lightning mapper maybe.
Yeah, so there's another instrument on the satellite called the Global Lightning Mapper, and that's something that's another completely different instrument. I'd have to look into that. I'm not familiar with the imager looking at that kind of stuff. It might be possible. I just don't know. Sorry.
Good question.
Yeah.
What's the target launch date?
Well, for the GOES,
Yeah, for the,
GeoXO, the 2031, 32 or something. It's we're not at this point. Like I don't have as much information because we aren't the launch or the spacecraft bus provider. We the optical payload, right? So we provide the optical payload. I believe Lockheed Martin provides the spacecraft bus.
the bus is defined, is it not?
I mean, it is defined. We know what we want to get, but
That was a huge mistake on Chris. It was not defined. And they had massive redesigns because of,
yeah.
and overruns were massive
What is
because of
the
that.
weight?
There's a two.
The existing ABI is, if I remember right, it's 800 or 900 pounds. It's not quite a half a ton, but it's really close.
Yeah.
So how big is the meter on that telescope?
Mirror of so it's. Would you like to say it was like a meter or something like that, or like talking about like how?
Big, is there 4 meters?
Yeah, so it's a 4-mirror and a
Yeah, I guess
stigmatic.
that's
So
what you're talking about, but they're not that big.
yeah, when I did it for my project, I sized it out about half a meter or something like that. When I sized the meters out for my project, it came out to about half a meter.
Okay,
Like
that
so,
sounds
that's
fine.
kind of they're not huge. They're not big.
It's pretty bright.
Bigger than ours.
You say our satellites are
Stationary.
geostationary at the equator, right?
Yeah.
Is the Earth perfectly round? If you tried to run a geo thing on
Yeah.
thing, you'd have to figure a difference in elevation or not?
Yeah. So what it is? So with geostationary orbit, it's more of it's more that it maintains like it's relatively stationary. And then we have, thrusters and whatnot to kind of, play around with. We have a lot of instruments on the satellite that allows us to do a lot of great pointing accuracy, such as infrared calibration targets and whatnot. We know we can kind of figure out like some of the micro adjustments we need to do that can be done pretty easily. So, but it just basically allows us to not have to use a ton of fuel to kind of just,
We'll actually do like Starlook. We'll actually look at very well-known stars. And we'll use that as like fixed points for navigation. And some of you guys probably remember Daniel Goleman. He was there a year or so ago.
Yeah.
Yeah, so that was actually that's why able to blanking. What star was that?
Betelgeuse.
Yeah, Betelgeuse. Yeah, that's how he
Like
was
the
able
dimming.
to. We got that great data for Betelgeuse that was useful for astronomy from what we were using for pointing accuracy.
Himawari.
Right. Yeah.
It's Japan.
Yeah. And some of the star trackers, fine sun sensors, you can get down to like 0.003 of a degree of accuracy, plus or minus 0.003 degrees. So you combine them together, you can get a very accurate system and know exactly your orientation.
So is there a GOES satellite all the way around the world, or it's just, I don't know, your
There's a-
diagram looked like we're just covering like.
There's like a goes east and a goes west. Maybe the graphic didn't do a good job of showing, but you can get like
I mean, like, just somebody covered China.
Just United States coverage.
We don't. It's by
Yeah.
satellites.
Well, and then Japan and then
With the
looking at
Himalaris.
so
Weather and stuff. That's
yeah.
what I mean,
yeah.
There's commercial Hawkeyes that look at that.
And I mean too, like we're talking about the geostationary orbit, but there's also all variations of low Earth orbit, mid Earth orbit satellites that can do imaging. So if geostationary is like serves a climate weather tracking purpose, but you have ones in other orbits that allow you have overlapping constellations, and you can get imaging that way too. All right. I'll thank you everyone. I really appreciate it. So bearing with me.
Thank you, Martin. What?
Thank you.
Appreciate that. So, great. We can build our own Hubble now. Thanks again, Martin. So we have a few pictures, Mike, and
What's your home video?
you must have a microphone. Oh yeah, plug it in. Plug it in. Plenty of room. Here you go.
Yeah, I just have two pictures.
Microphone, please. Right there.
Yeah, after many months of thinking about getting a smart telescope. A few weeks ago, I decided I'm gonna bite the bullet and put an order in for a Dwarf 3 and expecting the lag time to be about 16 to 18 weeks. And to my surprise, it arrived a week after I placed the order. So, but unfortunately, the weather has been absolutely terrible in the last 2 weeks. But nevertheless, I did one day last week, was able to take an image of the sun. Yeah, go ahead and can we enlarge that?
Yeah, sure,
Can
of
you
course,
blow that up?
absolutely.
Just want to show you.
How about that?
Okay, that's good. Uh, it's pretty amazing how the technology. There we go. It was in my backyard, and basically it's pretty much automated. That's 20 shots that were stacked, and then the final picture is, as you see, remarkable clarity, I think.
Yes,
And
it's a-
then
It's a white light image, right?
right, yes,
White light
yes.
image. Okay.
And I have a second picture that I took yesterday morning. Finally, they said at 4 in the morning the skies are going to be clear. So I actually got out of bed and went out to my backyard, set up the Dwarf 3, and took this. The technique is very similar. Phil, you know, but very similar imaging the sun and the moon. The machine automatically, when you set the parameters, it'll take 20 pictures in rapid succession and then stack them. And I was pretty amazed the detail on that. And I'm just getting my feet wet. I just started with this thing, but it's been a lot of fun so far, and look forward to learning a lot more, getting
Anything
more
else? Any other
comfortable with
images?
it. Pardon me?
Any other images?
I only brought those two.
Oh, okay.
Yeah.
You could put together a small group for
Yes. I
Or,
had that
yeah,
very same thought. Yes.
Sea Star.
Yep. Yep.
Yeah, red light shift.
Absolutely.
Okay.
Yeah.
Anyone
so
else?
Anyways, the price has gone up $5.99, but I think it's a real bargain. If anybody's interested. There's no delay anymore if you put an order in.
Hey, Mike, question. What happened you chose the dwarf for the smart scope?
Pardon me?
What were the criteria you used to choose the dwarf for the smart scope?
Oh. I tell you, I went back and forth and talked to, I saw club members using both telescopes and saw a lot of videos. I thought it was kind of a toss up. I think what was a deciding factor for me was the EQ mode that's built into this thing now. The Dwarf 3 has a larger aperture. The original Dwarf 2 had a 24 millimeter aperture. The new one is 35, which is nice, but then the EQ mode, eventually you're going to be able to take 120-second images, 120-second long image. Right now, 60 seconds, but they're very close to making that 2 minutes long.
Sea Star is
in the EQ mode.
Sea Star is going equatorial as well.
Are they?
Yeah, it's a relatively new option.
I don't think you can go wrong with either one. Just
They don't understand choreograph. It wrapped itself around overnight.
one thing good about Dwarf 3 is the plug is underneath the port.
Right.
So it goes I've seen. You and I talked.
Right.
I'd say either product.
So does it come with like a base that tilts, or you gotta buy that base separately?
It doesn't come with the price on it.
But to be able to filter that.
Oh, yeah. Well, yeah,
Just put that on the pan head of the tripod.
it tilts, yeah, the lenses tilt, and and the whole thing rotates.
So you get rough polar alignment, then you can fine tune. So the lens will rotate a little.
Yeah, it rotates and then it's.
Right,
up
but
and
still
down.
its axis somehow has to point at the North Star. So you
I
gotta-
haven't really been able to investigate that yet, but it's fairly straightforward if you look at the manual. And I think with the Torque 2, you've done it already, haven't you? Or are you able to do that? Phil?
Equatorial.
Yeah.
I played with the mode a little bit, but I'm restricted to 15 seconds.
Oh.
I don't want to spend that extra 2 minutes. But basically, it takes, you don't point it toward the north, well, you point it toward the North Star to start out. Then makes it, you calibrate it, it's almost straight up or to the south. So it doesn't use Polaris at all.
No.
It just does the plate solving and then tells you move the tripod right or left or up and down.
Actually, you can kind of turn it away.
Sounds like a drift method,
I don't know.
drift alignment.
Haven't done it yet.
Yeah.
But it weighs 3 pounds, which is so,
That's
so
nice.
light and portable, which is another factor, Bill, that I consider. But it was a toss up. Either way, was I think a good buy.
Yep, thanks.
Is it really?
Yeah. Or it's surpassed it.
Yeah, doors going up.
Getting bigger.
No, it's going up in price.
Yes.
Who are you gonna sell it? Celesтрons are gonna be equipment on the market here?
I don't know. We got a lot of it gathering dust right now. I don't know.
So welcome to the club.
It's cloudy.
I think there's a lot of.
It's cloudy anyway.
But as the tariffs spike, you'll find that these equipment, they go up in price.
Good, yeah.
I hope so.
Yeah, all right, a good thing. Anyway,
Thank you, Mike.
sure.
Pete, were you gonna give us
If
a,
anybody wants to look at. Take that out, 3.8.
We're impressed with what he gets for
Yeah.
Russ
low
is
money
gonna
for
zoom
the
in
price
right
point.
here.
as long as you're gonna talk?
Oh, I don't have anything to talk really.
Okay.
What is it?
Fast Newtonian.
Aptura Carbon Star.
What's the F ratio?
What?
F ratio?
With the coma corrector, it's 3.8.
Pretty cool. What's it weigh?
Not very much.
How much?
Like it's under 6 pounds, right?
I think it's around 10 pounds.
No images yet? Any images yet?
You know, Ed was out the other night and we were getting a bunch of coma on the outer parts. And I didn't have the, what they call the back focus correct.
Oh,
The distance between the coma corrector and the camera. It's supposed to, I guess it's kind of an industry standard of 55 millimeters. And I only had like 35 millimeters on there.
Oh,
Oh,
wow.
front, so it's got you on.
Oh, they got.
Oh, look, we'll see that.
there you go.
Oh, yeah.
Nice, clean.
And then it's got baffles in it too. Actually gives a pretty nice visual image. I was kind of surprised, but it's mainly just for photography.
So are you guiding on that? Or are you using guiding?
You using
No.
PhD2 or something else? Or is it all open loop?
You're not using guiding, you're using,
You know, I'm not using guiding. I'm just using the Osmandy mount I have. I did get the guide scope with it because I thought I might need that for polar alignment with the sharp cap. But it turns out that I got a wide enough field of view that the regular camera will do the polar alignment. And so I don't know if I don't really need that thing, but if I could put an eyepiece on it maybe to help
Could.
find something, but The sharp cap with the plate solving has really eliminated a lot of my issues with trying to find objects.
Bang them up,
What was that?
just bangs them in there.
Yeah.
We're just impressed with what he's got for the money, the machining and the quality of the focuser, and even the lens cap on the top of the screw on it. not
Yeah.
just a press on plastic.
Metal,
I mean, this Apertura out of China, just like a lot of those companies, just knock the socks off.
They got a bunch of guys chained to the workbench.
I don't.
well,
They're
they're,
doing a good job.
this carbon fiber tube is it's just perfect. And remember on carbon fiber, how expensive. it is.
Oh, yeah, it's exotic, you know.
I bet they're making these cheaper than an aluminum one now. I don't know.
They crash them up every week at Indianapolis, so it's not too expensive.
That's true.
What's the price on it?
So with the coma corrector, I think they're 1,100. They went up $100.
Mhm.
And I got scared the Chinese tariffs they're gonna go up to 1,500, so I ordered one. But
Pete, images next time. We expect images.
yeah, well, if it ever flares off again.
Yeah, that probably will never happen.
No, I don't.
Well, all right. Thank you very much. Hopefully, you'll be back for next month's meeting on tracking space junk. And
I have an image to show,
oh, I'm sorry, Mike. I didn't.
Mark.
Mark?
Yes,
Did I say Mike?
you said Mike.
My apologies. Sorry.
Don't worry.
Mark.
I have a brother, Mike.
I even have your name in front of me, and I messed it up. Go ahead.
Let me go ahead and try to share.
That question.
Yeah, there is a question in the chat. A question for Martin.
I don't know if you can see this image. I don't know if you have to do something on your end. I started to share.
Yeah, we can see it.
Oh,
We can see
good.
it.
I was in Tucson a few weeks ago and at Cat Mountain, and I was able to capture the blue horsehead on my small refractor.
And what constellation is the blue horsehead in?
It's in the
It says so right here, Scorpius. Yeah.
Scorpius.
Should read before asking. Yeah. Very nice.
Neat.
And it's close by. What was your exposure, Mark?
It's on there. It was 280 minutes, 1 minute exposures.
Oh, there it is, right up at the very top. Yes, 280. Yes.
It's
Must
a
have
small, it was a small refractor, 260 millimeter focal length.
Equipment. The Pleiades, is that what you use? The 68 millimeter?
That's correct. I have the larger one too, but I can't carry that on a plane.
Okay. So Pete, we expect an image of this. It's climbing. It's in Scorpius, and I see 4592. Summer's coming. Summer's coming.
So I spent about 2 hours this afternoon reading on the SharpCap software again.
Wow.
Apparently that software, there's a button on there to remove satellite trail.
Yes.
I knew the other thing, setting the lower limit, or upper limit of the pixels, but there's just a button there to remove satellite trail.
Nice. Yeah. I need to renew my license They just sent me a note, so I need to do that.
You can get a lifetime now.
Really? You see the question mark?
Yeah. Yeah, so that,
Let
that
me give
one's a
it.
little,
There you go.
yeah, so that one is a little bit tougher. I think with looking at redshift, you do have to know your in origin source, because the redshift, it allows, you have to kind of have a reference point to like tell. So Ben, do you study anything about the
Like
referencing?
some well-known object with some well-known lines. Joe knows all about this.
Yes, it's a
From the
spectroscopic
spectroscope,
problem.
yeah.
It's a spectral problem. You have to, like, if you can identify the hydrogen line,
Right.
you can figure out the redshift fairly easily from any known line. Polymer lines are fairly strong, so it makes it relatively easy. But there's an object that Phil, a galaxy that you took a spectra of and calculated its redshift, and everything is redshift so far away from its normal wavelength that it's difficult to identify. But once you get the idea of the shift, you can apparently find it fairly easily and then measure it. So you can, if you have the right equipment, you can do it.
Your mouth line, how far does that shift when you're approaching the speed of light? Can it be seen?
It becomes undefinable. So it's like, because you can't actually realize it once you get there. Essentially, so.
But it's a distance effect,
Yeah, it's
more than a
distance
speed
effect,
effect.
right.
It's still
So-
going the speed of light. The light is, but it's due to the Doppler effect. It appears to be longer. The wavelength is stretched.
Yeah, our phrase, so for our frame of reference is kind of what we're referring it to. You talk about the photon itself. The photon doesn't experience time because it's going the speed of light. It's going the speed of causality. But for us, our frame of reference,
Right.
we're sitting here or whatnot. That's what we perceive the distance and the red shifting and all that. But to that, the photon is like it's been emitted and it's already observed by the detector. Even if it's like billions of light years away, it's traveled.
Mm-hmm.
So it's really a frame of reference thing. So you're talking about the speed of light. So to the photon, it's like, it's a different frame of reference from us. When we talk about our stuff is all in our frame of reference.
Okay.
So Martin, I have another question. You touched on quantum mechanics.
Yep.
I'm not a professional. But the reason I don't understand why that makes sense is because every time an event happens, like, okay, I asked my wife to marry her. Oh, didn't ask. I, married the other girlfriend.
Well, one thing too.
But what I'm saying is, suppose said, gee, why can't I get into the universe where I win the lottery every time I buy a ticket?
So,
But you are.
One thing I want to get with
Yeah,
that.
but I'm not that person. I don't.
So one thing I want to get into with that too is a lot of times you talk about like Schrodinger's cat, right? The cat is both alive and dead in a box, or like the many worlds. Some of these examples were kind of made as like in a mocking way, like from the get-go. So whether we go with the collapse of the wave function Copenhagen or many worlds, we're talking about things that happen at the quantum level in a quantum type system, right? So we're talking fundamental levels like photon, electrons, muons, maybe some atoms and whatnot. The reality we think of like what we're doing now, we talk about one life you went this way, one life you went that way. Right. These are large interactions that involve trillions of interactions from air resistance to whatnot. So I think for me, which thing I struggle with is, like, yes, it maybe, let's say many worlds is true. What point in time though, when is it relevant for like us, our day-to-day life, as opposed to a fundamental thing that's happening at a quantum level, right? Like the Planck